Hello, good morning everyone. This is Ravi Kumar from Mechanical Engineering Department of ATME College of Engineering. I will be presenting you today an experiment to find out the thermoconductivity of a given metal rod. This is a part of the lab component prescribed in the VTU syllabus for 6th semester mechanical students under the subject heat transfer. It is an IPCC subject and it has got lab component in that, and that first experiment is to find the thermoconductivity of the metal rod, given metal rod. That's what we are going to do today. Right now, the objective is to find the thermoconductivity of the given metal rod, and how to find that. Before that, let us briefly recall our knowledge on the thermoconductivity property, because we all have already studied this in our theory classes very well, but yet it is required to mention it here. Thermoconductivity is a physical property of the material which tells you about the ability of that material to conduct the heat through the rod, right? Some metals conduct the heat faster, some metals conduct the heat moderately, and some materials conduct the heat in a very slow manner. What is the need to find this thermoconductivity of the metal rod? Applications of this property is like the requirement arises when there is a situation wherein you need to have a very good conductivity material for transferring heat quicker. For example, the fins of these air-cooled IC engines, where the heat has to be transferred quicker, then you have to use a material for the fins which is having higher thermal conductivity. And the other case, for example, if you take the handle of a domestic cooker, which you use for cooking food, the handle should be a very bad conductor of it, because the heat from the vessel to the handle, it should not come faster. It has to come very, it cannot stop the heat transfer, but it has to come very slowly. That means the rate of heat transfer through that has to be slow. So which material has got lower thermal conductivity, that type of material can be used there. So that is the intention. That is where the requirement of knowing this thermal conductivity arises. Okay. Now, how do we find that? We have got a small, before going to the setup, we just understand on what basis, what is the principle behind this. It is based on Fourier law of heat conduction, and we all know this equation very well. Q is equal to minus Ka dt by dx, right? All those things, we have used it many times in our theory classes. The same equation is used here, where Q is the heat rate of heat flow, K is the thermal conductivity, and A is the cross-sectional area, and dt by dx is the temperature gradient in the direction of heat flow. So that's what we all know this, right? This is the equation which we are going to use today. I'm not going in detail of this because we all have already understood this in our theory classes. Okay, and these of course some of the values of metals of thermoconductivity. Pure copper has got this value 330 to 385 watts per meter Kelvin, and brass 95 to 107, steel 20 to 45, stainless steel 55 to 65. Like that, for non-metals also you can find out, like wood, the concrete, everything, right? All those different materials, any solid materials can be, the thermal conductivity of any solid material can be found out. But here I have taken few most commonly used metals. How the property varies, you can see here. Some will conduct heat faster and some will conduct heat slower. The value K depends, as you can see in the equation. If the K is less, Q will be less. If K is more, Q means rate of heat transfer, is more. That's right. And better than copper, silver is even higher values. I urge you to go and find what is the thermal conductivity of silver yourself. I know the value, but I just want you to go and find and know that the silver metals thermal conductivity. Okay. Now, this is a setup what we have got in our lab to find this thermal conductivity of the given metal rod. As you can see, this is the complete setup mounted on a table, and this part where you can see you have got the rod here, but you cannot see the rod because it is completely woven around by a rope. ceramic rope, and that rope is going to help us to prevent the radiation losses and the convection losses, because we are mainly concentrating on conduction here. Hence that rod is inside this, and this rod is heated at one end, is electrically, and cooled at the other end using cooling water. And the rate of flow of cooling water is controlled by this flow meter here, right? By turning this knob here, you can increase or decrease the flow rate of water. So is the rate of heating can be controlled by our thermostat here, by altering the voltage and current values, which you can see here. Now it is switched off anyway, and I'll show you in the last slide where it is switched on. By altering this knob, I can increase or decrease the rate of cooling at this end. And we all know that this experiment has to be conducted under steady state conditions. What is steady state condition? We all already, of course, are aware of it. Again, I'll just briefly tell you about the steady state condition here. Steady state condition is nothing but the rate of heat supplied at this end is equal to rate of cooling at this end. That means the amount of heat coming per time, per second or per minute at this end should be exactly equal to the amount of heat going out at this end at the same time. Then the temperatures at different points on the metal rod becomes stagnant. They are different but stagnant. Maybe here it is 80 it remains all the time. Here it is 70, here it is 50, here it is 40, what is 30, maybe different values along the length, but those values at those points becomes stagnant. But heat is kept on transferring from hot end to the cold end. Okay, so that is the pictorial representation here. You can see here the same setup, and the temperature, we have to need to take the temperatures at different points on the metal rod like this. Different thermocouples are put here. Those thermocouples are connected to a digital thermometer here, you can see here, and this gives us the temperature readings. Okay, that's what we are going to conduct. I will show you that demonstration of how to conduct the experiment at the end of this presentation. Now, metal rod specifications are all given to you. It is all pasted on the panel, an experiment panel. The length of metal rod, diameter of the metal rod, the distance between the thermocouples, all these values need to be noted down. And T1, T2 to T7 are the temperatures at different points on the rod, and T8 and T9 are the inlet and outlet temperature of water. So these are the specifications, these are the readings what we are going to take, and this is the procedure. What is the, it's a simple procedure, not much of expertise is required to conduct this experiment. Note down all the specifications as shown in the previous slide. Switch on the mains, take the power to the panel, and switch on the heater and maintain a steady flow rate of cooling water. As I said, it depends upon the rate of heating. Rate of heating can be set by thermostat, as I showed in the previous slide, by altering the voltage and current supplied to the heater, and by altering the flow rate of water, we can try to achieve the steady state conditions. And once the steady state conditions are established, the values like the voltage, the current, and the temperatures at various points need to be noted down onto a tabular column. Okay, so this is the tabular column where we are going to trial 1. This is the trial 1. We are going to note down all the values: flow rate, voltage, current, temperatures on the different points of the rod, water inlet and water outlet. This is one experiment. Again, you change the rate of heating by changing the voltage and current. You can take second round of reading. Similarly, for third rate of heating, you can take third trial reading. The intention of doing this is to arrive at a more correct value by taking the average of 3 experiments. You can just arrive at a correct, precise value. That is the idea. Now, after knowing those, noting down the values, how to calculate what you are going to, how do you calculate the K value? Which equation do you use? We all know the Fourier equation. Again, the heat, Q is calculated using V into I, voltage into current. The rate of heating what the heat is supplied, that is got by this equation. Q is equal to V into I, voltage into current. Both we have noted it down from the experiment. And the area of the cross section of the metal rod need to be found out. That is nothing but pi d square by 4, because it's a circular rod, and the diameter of the rod is given, and you have to find out the A. And the next value is the temperature gradient, dt by dx. That we are taking from the graph, which is drawn along the x-axis is the distance on the rod, right? And along y-axis the temperature of that point. For example, T2 is the temperature at the first point of the rod, T3 is the temperature of the second point, T4, T5, T6 and T7 along the length of the rod. Right? You can see the temperature is decreasing. This is the heating end, this is the cooling end. The temperature changes from heating end to cooling end in this pattern. It is decreasing all the time. The gradient is like this. At a very straight portion of the curve, we are going to take dt and dx value, temperature and distance value, and dt by dx is going to be calculated using the graph. And that is taken to this equation, where we are going to substitute in the Fourier equation q is equal to minus ka dt by dx. The same is written for k as k is equal to minus q actual a into dt by dx watts per meter Kelvin. Why this minus equation? I have explained it in the theory class. You just refer those things. Okay. Now my intention is to find out k. To find out k, I need q, a and dt by dx. All these three I know already. I will substitute all those things and find out k value. For one rate of heating, I will find out. For second rate of heating, again I will find out the same procedure I will follow and find out the k value. And another trial I can make. And all the three trials average value I take, and finally I declare the result. So this is how we are going to find out the thermal conductivity of any metal rod given to you, and finally you are going to arrive at the result. Now let me just tell you how to conduct the experiment physically there. It's a small demo video where I'll be giving the commentary here, and I'll be showing you how to conduct the experiment. Okay. So this is the whole setup here, the complete panel, and the metal rod is placed here, right? As you know, it is wound around the ceramic pool, heating end and cooling end, right? And the cooling water is flowed through the pipes here, and the flow rate of that can be adjusted using that knob there. You can turn it to increase or decrease the flow rate of water. Similarly, the rate of heating can be controlled by this dimmer stat. By rotating this knob, you can vary the voltage and current, thereby rate of heating here. And this is the place where we are going to treat the temperature. So let me switch on the panel. Power supply has come to the panel. Now heater is switched on, and now the heater is being heated. The heat is supplied to the rod from the heater end. The intensity of heat can be controlled by this dimmer stat, as I said. By varying that, I can increase or decrease the rate of heating, which you can see voltage and current values here. Similarly, the heat flows through the rod and reaches the other end. From the other end, I am going to take the heat out using the cooling water by adjusting the flow rate here, right? And here the temperature readings at different points on the rod. As I said, thermocouples are placed at different intervals, equal intervals here, you can see here. And these rods, these are the wires which are attached to the thermocouples, and they will let us know the temperature at those points on the rod, and that can be read on the digital meter provided here, right, from this end to that end. Okay. Now the steady state has to reach, as I said, after reaching the steady state, you just come here, note down the voltage and current, and also the flow rate of water, and the temperatures at different points can be found out using here. There are two buttons, the channel selection buttons, plus and minus. You just press one button, you will get the temperature at one point, next button, temperature of the next point, third point, so on and so forth. When all the readings are taken, we go back to the calculations. So this is how we are going to find out the thermal conductivity of a given metal rod. Thank you.